All right, everyone. Hope everyone's doing well. Hello for us. Let me see here. Hope everyone enjoyed the narwhal while waiting. I'm doing well. Thank you for asking. I'm going to close this and we will start on the lecture. I'm feeling pretty good. I'm a little bit blah, so I'm not 100%, but I feel well enough to give the lecture. It's not COVID, thankfully, but this I'm just top of some soreness and stuff, but it may be a cold or something. All right, so if we look at the schedule here, you'll note. Also, I guess as a precursor, I mentioned it already in the description when I posted the link, but I do want to make sure everyone knows this is being recorded. So, please be aware of that. So if you do have a question and you ask it over the voice chat, then it will be recorded. I will post it to YouTube, but it will be unlisted, so people can't find it without a link. I will post a link to it for those that are taking it online and or could not get here or join us today. So the topic of this week is going to be the grammars and context-free languages. So that's with the Chapter 4 material. We did discuss the fact that there are languages that are not regular, correct? And we realized that, Claney's theorem, we discussed Claney's theorem for regular languages. We also discussed the pumping lemma and how regular expressions have that particular property that is covered by the pumping lemma. If you do have, I guess the other thing, follow up to what I just said, if you do have a question and you do want me to call on you, you have to use the toggle button. There should be a toggle button, or you can ask it in the chat always, that's for sure. I will read those. But if you're okay with being heard and recorded, you should have a panel that allows you to press a hand raise. So it says something like raise hand or something like that, or it's a picture of a hand. So you can press that and it will show a little icon next to your name in my participants list, and then I will be able to call on you. But make sure after you've asked your question or after you've been called on that you turn it off, so I don't think you have a question, another question, or a perpetual question or something like that. If you can't find the hands up, there should be a hands up, but there a hand up, but there might be a thumb too, like a thumbs up, but I'd rather people not use that. if they can avoid it. If you can use, if you're agreeing with it, then thumbs up makes more sense. But if you do have access to the hand raise, that would be the best thing. Okay. I don't know what other images you have because I'm usually on the presenting side of Zoom meetings. So, okay. So let me see here. Where's context free? Okay. I guess before we get started, are there any questions before we talk about this week's material? We'll do a quick review and then discuss some of the material for this week. Hopefully we'll be back in action in person on Thursday, but I guess it's still possible. I might still feel unwell, but we'll see. If I feel absolutely terrible, I do have recordings of this material as well that are from previous semesters. So that would be like the last ditch effort to make sure everyone gets the material. But as you can see, pretty much when I revise it, I will change I usually remember to change, if there's any significant revision, the semester information at the bottom. But as you can see, it still says summer 2023, but that's because the material really hasn't changed. Okay, so we talked about how to describe a regular language using 3 different entities, really. So we've got regular expressions, finite automata, and transition graphs. And we talked about Kleini's theorem. So slide 3. We discussed how you can take a particular, say, for example, transition graph and convert it to a finite automaton, because finite automaton to transition graph is trivial. We talked about that. We talked about how to take a transition graph or finite automaton and you can be given a regular expression and find a transition graph or vice versa. And then by nature of what transition graphs are, you could also have a finite automaton and get a regular expression out of that fairly easily as well. So we talked about that process. We talked about Kleini's theorem and the process of doing that. The 2 major things that we focused on were, if you're given a transition graph, how do you remove the stuff that makes it not a finite automaton, turn it into a finite automaton? So it says we know that transition graphs are non-deterministic, finite automaton are always deterministic. So that was our major problem with this. We can have things like lambda on an edge in a transition graph, and we can have things like entire strings on an edge with a transition graph, but you cannot have that with a finite automaton. We talked about how to create group states. So if you have a state branching off into 2 other states, but it's the exact same input that leads to those 2 other states, you can collapse them into a group state. Same thing if you have lambda on an edge. If you have 0 to 1 and then 1 to 2, and you have a on the 0 to 1 edge, and then lambda on the 1 to 2 edge, that's almost as if that edge doesn't exist. So you can kind of, just like we slide on over, you can actually compact it down and make it a group state. Okay. Okay, we talked about also how to make intermediate states and split them apart, essentially. That's kind of the opposite of making a group state in some respects. Excuse me. So we did some examples with that. I use an intermediate or intermediary table, which is not in the book. It's just kind of a handy little trick I use to get my bearings and to remind myself of things. You do not have to use that table, but you will have to do things like filling out the final table where there are, for example, what does the final finite automaton look like? And you should, from that table, if you need to, be able to draw the state transition diagram of the finite automaton. So we did a couple examples of that. That should be reasonably sufficient as far as the quizzes and tests are concerned. This is what the quiz this week is on, essentially, as well. So let me see here. we also talked about how to take the transition graphs and turn them into regular expressions. We basically collapse it until it's on this kind of bizarre hybrid chimera type machine that isn't a transition graph, isn't a finite automaton. It's just a machine. And it doesn't really matter because we're trying to get everything down to the start state, end state, and then collapse it so that we get a single regular expression on one edge is our ultimate goal. And then we throw away the machine. We don't need the machine at that point. So we just wanted the regular expression. Okay, and then it's already kind of included in the previous material, so I'm not explicitly saying, hey, convert a regular expression to a transition graph, but it's assumed you know how to convert or create a finite automaton from a regular expression, so that kind of is trivially included in this as well. We talked about the fact that non-regular languages exist because of the pumping lemma for regular languages, that regular languages have to have this particular property of the pumping lemma. But if you can prove that a language definitely does not have this property, then you know it's not regular. Okay, so we talked about how to do that. All right. Okay, so we did revisit this one language, A to the N, B to the N, and we asked, is that regular? And the answer that we got, that we realized, is that this thing can't be regular because it violates the pumping lemma for regular languages. We can also see that because of the fact that it has to keep track of how many A's, so it knows how many B's, then that is memory that the finite automaton does not possess. Therefore, since finite automata are equivalent to regular expressions, that means that this thing, A to the N, B to the N, cannot be regular. Okay? All right, then we finally discussed decidability, and decidability was the one we're focusing on is, can we determine if two finite automata accept the same language? So we discussed the fact that you can take these finite automata and essentially you're applying the operations to the language itself, but you can think of it as applying it to the particular machines. And you can apply set theoretic operations on it, such as intersection, union, and complement. Okay. Can everyone hear me okay? Any thumbs up? Okay, good. Getting several thumbs up. Okay, sounds good. All right, good. Probably should have asked that at the beginning, but so I started to give a lecture once, and I probably went about 3 minutes into it, and then realized that my microphone was muted. So that was cool. Thank God I have a PhD. That solved everything, didn't it? No. So laugh emojis are great too. I like those. So thank you. It shows me people that want A's. That's really what it does. So the decidability to determine if they are the same language, we said that if we create this complement machine, so it's this hypothetical machine made of the complements of the other languages, it's got an intersection complement unioned with another intersection complement, and if we can create a machine like that, that means that machine has certain accept states. And what that implies is if any of the accept states overlap with one of the machines, then that means that they can't represent the same language. Now, the reasoning for that, again, is the first part of this, there's two parts combined with a union. The first part in parentheses is L1 intersect L2 prime. Okay, L2 apostrophe. So L1 intersect L2 prime. That means things accepted by language 1, and they're in the complement of language 2, meaning they're not in language 2. So if you can find an intersection, that means they both have it, meaning that L1 has it, but L2 does not. Or if you have L1 does not have it, but L2 does, that means obviously they aren't the same language. Because if they were the same language, they would accept the exact same words. All right. And then we give examples of that. So I said you should be able to do this on a test. The other possibility is I may just give you two machines and say, okay, find L1 union L2, or find L1 intersect L2 prime, and that's all you need to do. Or L1 intersect L1 prime. That would be hopefully an easy answer. But there are other possible questions I could ask related to that with intersections, complements, and unions. So just keep that in mind. All right, then I gave a couple examples, and we were pretty much done with it. So that was basically the review of last week's material. Are there any questions about last week's material before we move on to this week's material? All right, so we will move on to the next set of material. We'll get through some of these. All right, grammars and context-free languages. So we've largely focused on recognizing languages with finite automata and describing languages. A grammar is used to generate a language. This is what we will focus on in this chapter. So additionally, we will explore context-free grammars, which are a more powerful way of describing languages than regular expressions and regular languages. So the question is, will we be asked to write regular expressions as well as others on the first test? Yes. Yes. Almost, well, yeah, pretty much 100%. You might have a description of a language and say what would be the regular expression, or you might have a regular expression given to you and you say, what does it mean in English? So, all right. So we have to have, if we have this context-free grammar here, then we probably have a corresponding machine, we would think. So there's an automaton that actually corresponds to the context-free language, or CFL. That one is capable of recognizing a context-free language, namely the push-down automaton. That is the new automaton that we will learn about. So finite automata are only capable of recognizing regular languages. Okay, since not all context-free languages are regular, we need a more powerful machine to help us. Okay, so the parts of this lecture are the Bacchus normal form, okay, or Bacchus-Nauer form, that is BNF form, parse trees and ambiguity. We'll talk about that under the context of headers. We will also talk about context-free languages, so designing a context-free grammar to generate a given context-free language. We will talk about Chomsky normal form. You won't be required to do any major conversions with that, but you should know what it is and what it's for. And we will, of course, talk about push-down automata. So grammars. So while automata are used to recognize languages, grammars are used to construct or generate languages. They're the primary tool used in construction of programming languages, scripts, etc. So at some level, we would say that the grammar deals with the syntax of the language, but it doesn't deal with semantics or meaning. So syntax error at compile time in a programming language is a violation of the grammar of that language. You may have heard that before. And fatal runtime errors and logic errors are semantic errors. So those are typically the result of something going wrong that doesn't violate the grammar of the language, but it does do something wrong in memory or produces an incorrect result or things like that. Those are different kinds. Those are basically the three types of errors that we have in programming: syntax, runtime, and logic. So specifically fatal runtime errors and logic errors. So grammars are involved in all of this programming language stuff. Okay, so consider two sets. We've got a set T and a set N. The set T is a set of terminals. These are called terminals. So these are like the actual literals in the language. So for example, our set of terminals consists of John, Kiyumi, eats, sings, and talks. Those are the terminals. We also have non-terminals, which are like variables. Okay, they're also called variables. That's another word for them. But the non-terminals, N, consist of, for example, S, noun, verb. So this might be a way to split these up. So a set of terminals, set of non-terminals. The second set, N, non-terminals, are similar to variables in a programming language, and they're ultimately replaced by terminals in a given production. So, for example, if S is the sentence non-terminal, meaning where you start, and you say something like S yields noun verb, I could then pick something to replace the noun. Now, the way we have it, we don't actually have any rules or descriptors telling us which one of these are nouns or which ones are verbs, but we'll forget that for a moment. We'll play by those rules. But these are definitely terminal symbols, okay, or non-terminal symbols rather. So noun and verb are definitely non-terminal symbols. Noun, I could go from left to right and replace the noun with John, because that's one of the nouns here. And then I could replace the verb with one of the verbs that is one of the terminals as well. Okay, so you could have two subsets. That would be another way to distinguish them. But you could replace noun with John, verb with eats. John eats. John eats too much. That's why his sugar's too high. A grammar for a language is a collection of three things. A finite set of terminal characters, sigma. Okay, so that one shouldn't look too strange, because that's the exact same symbol we used for alphabet. And again, that's not coincidental. So the set of terminal characters is sigma. We have this new concept of this thing called a non-terminal, which we didn't really have in regular expressions. So we have a finite set of non-terminal characters, gamma. Okay, that's the thing that looks kind of like a I don't know, a snake on its head or something. A very, very stiff snake, of course, or the trunk of a brontosaurus. I like that better. But then you've got sigma, then you've got capital sigma, capital gamma, and then one of the symbols is denoted S for the starting non-terminal. That's just a convention. That's pretty much what we follow. It doesn't necessarily have to be, but it is something we follow most of the time. When it's possible, we usually capitalize the non-terminals to distinguish them from terminals, and a finite set of rules. So the grammar consists of a finite set of terminals, finite set of non-terminals, and number 3 is a finite set of rules, also called productions, for replacing expressions containing non-terminals. So ultimately, if you get a word, it has to eventually get replaced by a terminal symbol. Otherwise, it has a non-terminal in it, which basically has to be eventually converted to a terminal. That's kind of the idea here. Otherwise, it's not really a word. So a word or string in the language is going to be ultimately a concatenation of terminal characters. Okay, but the rules could definitely involve non-terminals generating terminals. Okay, so a little more formal definition here on slide 8. A context-free grammar, or CFG, is a grammar where all of the productions, okay, remember those rules that produce or convert non-terminals to terminals. So all the productions are of this form. So we have the form where on the left you've got an arrow in between two things, and the thing on the left of the arrow, so it kind of acts as an operator. The arrow and the operand on the left of the arrow has to be a single non-terminal, not two non-terminals, not a non-terminal sandwiched between terminals. It has to be just a non-terminal by itself. And then the thing on the right, the thing that gets generated or produced by that non-terminal, is a finite string of terminals and non-terminals. So a context-free language is a language generated by a context-free grammar. Okay. The process of using these productions or rules, or production rules, doesn't really matter, to convert the starting non-terminal S into a string of terminals is called a derivation. Okay. So you're deriving a word out of the original non-terminal or terminals. Okay. So that's called a derivation. We use the symbol arrow. So there's a variety of different arrow symbols that could be used. But the one I use here is basically just a plain old stick going to the right and then arrowhead on it. This indicates that a production has been used. Okay. Now here's our example, CFL, our context-free language example 1. We have sigma consists of two different characters that are possible. So we have A. I got a little too Greek there. So we have A, and we also have lambda, the empty string. So those are the only two characters in this alphabet of terminal characters. So we've got sigma is A and lambda, and gamma, the set of non-terminals or variables, is just S. There's one element in that set. So there's two in the set of terminals, one in the set of non-terminals. And we have two production rules. Remember, to have a complete grammar, we need the terminals, the non-terminals, and the production rules. And that's what we're doing here. So we've got S produces SA, okay, or S produces lambda. So the first one tells us S produces SA. There's a little bit of kind of a recursion here, like a structural recursion going on here. So S arrow SA, or S produces SA, means it produces a non-terminal on the right, followed by the terminal A. Okay, so using the above, we can derive different strings. Okay, these are just three examples of strings that we could derive. There could be many, many of them, infinite many for this actually. But using the above, we can derive S yields lambda. Okay, I know it's still using an arrow, so that might be a little bit confusing, but in this case, it's not a production rule, it's an actual derivation. So the thing that you end up with on the far right is going to be an actual string that is a valid context-free language for this particular language. Okay, so S can yield lambda. What lambda means is it's an empty string, so that means you could have no characters at all. You could also have S yielding SA, okay, but we're not done yet. So if S yields SA, we could then make the S in the SA produce a lambda, so then you get lambda A, and then that's just A by itself. You could also get another derivation where you start with S again, so that's always the start symbol. So you could generate SA, and then with that S in SA, you produce another SA, because we can keep applying that first rule, S yields SA. And then once you get that, let's say we decide that that S now can yield a lambda, and then it's lambda AA, so we just end up with the string AA. If you follow it, you could probably conclude that we could generate words like lambda, A, AA, AAA, AAAA, etc., etc., etc. But that also could be represented as A star. And since the Kleene star is part of regular languages, this might bring a little bit of confusion, because I said we are dealing with potentially languages that aren't regular, but that's we will see those, but this is not one of them. The reason we're giving this example is because it's simpler, and A star is absolutely a regular language, but it's also a context free language. Okay, so context free, if you did a Venn diagram, you could see context free is actually outside of regular languages. So, or not outside, but sorry, regular language as a circle is inside of context free languages. Okay, so all regular languages are context free, but not all context free languages are regular. This just happens to be an example where it is in fact also regular, but we're looking at it with a context-free grammar. This is just an alternative way of describing the language, a different way to model the language, right? There's our word, our magic word for the semester. Our model for the language is the context-free grammar, which consists of the terminals, non-terminals, and the production rules. Whereas down here, you would have your, with a regular language, you could just say, well, I just need, a single terminal A, and I can just apply a star to it. So I get my regular expression. So just different ways of describing something. Example 2, in this particular example, a little bit more complicated. We have sigma, the set of terminals is A, B, and gamma is the set of non-terminals. That gives us an S, and we've got three productions, three rules. So we've got S yields AS. Okay, this is capital S in each case. Capital S yields lowercase a S. So the A is a terminal, the S is a non-terminal. We could also have S yield BS. Okay. S can also yield ABBA. So that last, production rule does not have any non-terminals in it. So there's no variables in that last one. meaning that we can eventually stop. If all of your production rules only had terminals and all had non-terminals in it, so each production rule had at least a single non-terminal in it, at least, that would mean that you couldn't actually generate any words with that language. You would always end up with a terminal that can't, or a non-terminal that can't be derived to a terminal. So that would be bad. We can't have that. So eventually you have to have some sort of terminal or string of terminals like we do here. So you've got S yields AS, S yields BS, and S yields ABBA. So that last one is all terminals. So using the above rules, productions, we can use those to get derivations. So which derivations, or what are some of the derivations that we could get? Obviously, you could get an infinite number of derivations, so it is an infinite language. But we also said that there are regular languages that are infinite, so this still could be regular. We don't know yet. So let's look at it. So S yields ABBA. So that was our last production rule, could give us that derivation. It just gives us those characters concatenated together. We could also get S yields AS, which is AABBA. Okay. We could also have S yields BS, which is BABBA. We could have S yields AS, but then we choose to take this S and on the end of the terminal A that we already have, we generate another AS by the first production. Okay. So then we can take that last S. So we've got AAS, right? So we've got AAS. We can take that S and then we can generate ABBA. So we have the two A's followed by an S, and then we can just take it the rest of the way and use it as a terminal or to generate a terminal. So you end up with AA, ABBA. You could also do the same thing with kind of going the B route. You could go back and forth, in fact. But if we go the B route first, we could go S generates BS. You then have that S generating an AS. So we kind of switched it up this time. But we could have gone with the BS. We could have gone with any of them, right? But we have BAS. Now, what do I do with that last S? Maybe we decide to say, okay, well, let's go to the terminals and go ABBA. So now I have BA, ABBA. So it's looking like I can have any number of B's or A's at the beginning as long as the string ends with ABBA. Okay. So if I had just described that in English to you, instead of giving you all these production rules, I say all words in a particular language start with any concatenations of A and B, including 0, followed by ABBA. You could probably come up with the conclusion or conclude that this could be expressed as a regular expression because we have seen regular expressions like this before. So we know the ends in ABBA is part of it, but also any concatenations of A's and B's or A's or B's, including 0, is just A or B in parentheses star. So we apply the Kleene closure on that. So the language of strings using A's and B's, this is also regular because we can use the symbols involved with making a regular expression. Okay. A little before we look at slightly more complicated things. Are there any questions before we move on? Okay. So this is slide 11. Bacchus normal form. It's also called Bacchus-Nauer form after Peter Nauer, who also worked on it with John Bacchus. But some people, it's always BNF, but some people say Bacchus normal form. Some people say Bacchus-Nauer form, Nor, which is N-A-U-R. That's the guy's last name. So throughout computer science and software engineering, the topic of normalization comes up frequently. You will hear this a lot if you take a course on databases. I would recommend taking a course on databases. I don't think they're required anymore here. CIS 421, I think. I think depending on your specialization, you don't necessarily have to take it. I would say if it's an option, I would probably recommend taking because database stuff is everything. So we can think of normalization as simply removing redundancies and reducing something into a more standard compact form. So That's a very loose definition. There's more formal definitions depending on what you're dealing with, but BNF form is absolutely used in databases when describing entities and things like that. So BNF form, named after John Bacchus and Peter Nauer. The form is a slight variation on what we've used thus far, except we allow for saving space using it looks like a vertical pipe or vertical bar. That means or. We just need one of them. You don't need two like you do in Java or C++ or C#. So examples would be n yields stuff1. Okay, now stuff1 could be a single character, it could be an entire string, it could be lambda, it could be a lot of things. But if we have n yields stuff1 and n yields stuff2 as two production rules, we can actually reduce those using Bacchus normal form by putting an or in between them and putting them on one line. So it could say n yields stuff1 or, that's the vertical bar, stuff2. Now, if you are asked the question on a test, let's say you have this n yields something and I have stuff1 or stuff2 or blah, blah, blah. You could even keep going with the or symbol, of course. But if I have this and I say, how many production rules are there? Don't say one. Even though there's one line, you can clearly see that n can yield stuff1, but n can also yield stuff2. Okay, it can create stuff2. So that means there's actually two productions going on here. All right, BNF example. So the grammar from earlier, S yields AS, S yields BS, S yields ABBA. We can actually reduce this using this grammar using BNF. So S yields AS or BS or ABBA. So that can all go on one line, but it means exactly the same thing as the three production rules separately. All right. Okay, here's a third example. So this one's a little bit different. So let's look at this one. Okay, wait a minute. Does plus always mean or? Plus means or for our purposes. Yes, it will mean or typically when dealing with sets. With regular expressions, the plus will mean or unless indicated otherwise. Okay. So we will use BNF initially with our CFL example, our context-free language example. Let sigma equal the alphabet. It's got three characters this time, so A, comma B, comma lambda. Okay, and then let the non-terminal symbols gamma equal just S. So again, we only have one non-terminal, but we have three possible terminal symbols, A, B, and lambda. And we see that we have two productions, but they're on one line here. S yields ASB or lambda. So again, S yields ASB or lambda. So you can see that this time we have the non-terminal symbol, the variable, sandwiched in between two terminal symbols. Okay, so it's a little different from what we've seen before. So using the above, we can actually derive the following. You could say S yields lambda, okay? So it can create lambda, that's empty because that's one of the production rules tells us that directly. We could also say S yields ASB, or S produces ASB, and then we decide to make the S in between the A and the B a lambda, so then we get A lambda B, which is just AB, because lambda is the empty string. We could also do S yields ASB, which yields ASB, because that middle S in the original ASB, we just said, let's run it again. We'll loop on it and make another ASB. So we did that. So now we have AASBB. And then maybe we decide to take that S and now use the second production rule and create an empty string, a lambda. So now we finally get AAA lambda BBB, which is just AAA BBB. So it appears our language is growing from the center. That is, we have AB, AABB, AAABBB, but you can see that this language is the A to the N, B to the N that we saw previously. And this is not a regular language, okay? So you cannot come up with a regular expression to generate this language that we did generate with this context-free grammar, okay? So you can see that context-free grammars can generate any language that's regular, but they're even more expressive in that they can generate languages that are not regular. And this is one example, A to the N, B to the N. So we see that our grammar could generate non-regular languages. Okay, another way of representing derivations of words from a grammar uses a parse tree. So this is also called a syntax tree, generation tree, production tree, and derivation tree. The tree starts with the starting S non-terminal at the root and illustrates the production to form a single string. So parse tree is for a single string. That's a key thing because there's also language trees or total language trees that we'll look at in a minute. So for this, if I want to look at the derivation, if you see the derivation S yields SA, and then that generates BA, I can create a parse tree. In this little image here, you'll see that there's an S at the very top. You'll see that there are two branches coming off of the S. So it's a binary tree potentially. It could actually be more than a binary tree, but in this case, it's at most binary. So we have S at the top, and then a left branch and a right branch. The right branch has an A, which is a terminal symbol. The left branch is another S. That's because if you read that second part of the production rule, S yields SA, if I read it just using level order traversal on this tree, I can see that it's just, again, S yields SA. But eventually we do want to get another leaf out of that. So we end up with BA because the S generates the B, and then you can read just leaf traversal. So you say BA, and that ends up being our word that's generated and represented by this parse tree. Another example, parse tree, is what if we have terminals AB and we have non-terminals SX, Y, okay? We might have maybe a particular derivation from a set of rules being down here. S yields A, X, Y, B, and then X yields A, Y yields BX. You notice that since one of them can eventually get to a single non-terminal or a set of non-terminals by itself, in this case it's only one. Since that is the case, then we know that this could be a valid grammar. Okay, so the derivation that we're looking at here with this parse tree is S yields A, X, Y, B. And remember, the X, Y, and the S are all non-terminals. So A, X, Y, B yields A, Y, B from the rules down here, because we took the X and created an A. And then what do we do with the Y? Well, the Y, we make a BX, so we end up with A, B, X, B. And then that X gets replaced with an A. Okay, so we end up with A, B, A, B. And that's exactly what happens with this tree over here. The first level shows me the first part of the production, A, X, Y, B. And that's exactly what I see in the derivation. Okay, so the second part is A, Y, B, which is A, Y, B, and then A, B, X, B, A, B, X, B. And then finally we have A, B, A, B, which is all the leaves. A, B, A, B. Okay. Now, there are also trees called total language trees. This is another model. It's another way to show all the words in the grammar in this case. This is called a total language tree. So the interior nodes, which are non-leaf nodes, non-root, contain working strings. A working string is a string that can contain both terminal and non-terminal characters. For the following CF grammar, draw a portion of the total language tree. So this right here, we see three rules, and we're kind of assuming we're working with AB as the alphabet. So we've got S, which is by convention the starting point always, even if there are other terminals available. And it's usually involved in the first production. So S yields AB or lowercase a, capital A, meaning we can get two non-terminals right next to each other. That's one possibility. S can yield AB, or it can yield a lowercase a followed by a capital A. Okay. So S yields an AB, or it can yield a lowercase a followed by an uppercase A. Okay. Now, what about past that point? So we see it in the diagram. S has AB on the left and AA on the right, lowercase a, uppercase a on the right. And then what about if I'm going down the route where I went to a capital A, capital B? Well, capital A, capital B, I have an A at the beginning. The only thing that can generate is a lowercase a. So I have the capital AB having a left child, lowercase a, b, and then it has a right child, capital A, lowercase b, lowercase a, because the B generated lowercase b, lowercase a, and we still have AB. We also can get ABA if we keep going here, and ABA if we keep going there. And then finally on S's right side, AA, we can get AA, lowercase a, lowercase a. And then you can get obviously arbitrarily more complicated total language trees. This one, for example, is much larger. This one actually, you could just keep going. This could be infinite because we have S yields AAS, yields SB, yields B. Since there's one or more productions that also have an S in it, this is an infinite language. So obviously we can't draw the whole tree, but if I say draw the portion of the total language tree, including all strings of less than 5 letters for the following grammar. So when it generates full strings, like all terminals, with less than 5 letters, then we can stop. So we start with S, we can end up with AAS, we could do a B, we could do SB. I just changed the order here, or we changed the order here because the B is terminal and we need more room on each side. It doesn't really matter where you put it as long as it's a direct child of S. And then I've got a terminal there. We got the B as a terminal there. So what do I do from here? So the S can yield AAS, but it could also yield SB. All right. So S yields AAS. And since S yields AAS, the AAS, that S at the end needs to be handled. So all 3 of its children, you'll notice, have AA at the front. That's because that part's in stone by this point. But the S, again, could be, again, AAS, SB, or B. Okay, so AAS in this case, it could be a B here, so we get a terminal AAB, or we could get AASB. All right, and then we could keep going, etc., etc. Ambiguity, you probably have heard people use this term in different contexts, but in the context of the languages, the grammars we are dealing with now, sometimes the effect of productions is not unique in that a different sequence of productions can be used to generate the same string. We actually saw that a minute ago. Up here, we saw that AB went through 2 different routes and still generated the exact same string on 2 occasions. So that if a string has 2 distinct parses, okay, that's called a parse, then the string can have 2 different meanings, okay? So even though we're not getting deep into the semantics, it could mean that there's 2 different ways to get there, meaning it could have 2 different meanings, okay? So this is an undesirable property of grammars, okay? Because of the fact that it could have 2 distinct meanings. So the grammar that is like the one we just looked at that can produce the same string but through multiple paths is called ambiguous. So a grammar is ambiguous if there exists a string W which can be generated with 2 distinct leftmost parses. Okay, those are the types of parses we've done so far. So here's an example of ambiguity. We have consider the following grammar. Let sigma equal, it's 1 single character in our alphabet that we're dealing with here. So we've got sigma is just the A, and then gamma is just the S. So we just have S's and A's. But we have 3 production rules. We could have done this in Bacchus normal form, which probably would have been better, but S yields AS, S yields SA, or S yields A, okay? And we can look at several derivations down here, which is no surprise because there's 1 character in the alphabet, 1 letter in the alphabet. So we've got S yields AS, yields AAS, yields AAA. Also, S yields AS, yields ASA, yields AAA. The third line on slide 20 is S yields SA, yields ASA, yields AAA. And then we have a 4th one, S yields SA, yields SAA yields AAA. So for just that single word of 3 characters long, there are 4 separate, 4 distinct leftmost derivations. Okay. This is meaning that we're kind of reading from left to right, replacing the non-terminals. So that's leftmost. Now that means that this grammar is then ambiguous. Okay. Are there any questions so far? Okay, we'll do a couple more slides. We're not going to get through this whole section yet. We will save most of the fun for Thursday. So context-free grammars. Again, as a review, okay, can we call it ambiguous when we see it has 2 ASA or we reach AA? You can give an example and then say, okay, we know this is ambiguous now, but you probably will get a pretty good intuition for what is ambiguous, especially with something that obvious. So yeah, the question was, can we call it ambiguous when we see 2 ASA or when we reach AAA? Can we call it ambiguous? So I would say give an example, or give an example when you get 2 different derivations, just to prove that you can do it. And then once you do that, then you will have given, and it's an existential proof. It's one of the easiest kinds of proofs, is just to provide actual examples. But you can get an intuition without even going through the process that something is ambiguous or not. Okay, so we did say that context-free grammars context-free grammar is a grammar where all the productions are of a non-terminal on the left side, yielding a finite set of terminals and non-terminals on the right, correct? So we can state our process of describing a language using a grammar differently by generating each string of that language in the following manner. So you can write down the start variable. It's the variable on the left-hand side of the top rule, okay, unless otherwise indicated. And you can find a variable that is written down and a rule that starts with that variable, replace the written down variable with the right-hand side of the rule, and then repeat step 2 until there are no more variables remaining. That's pretty much what we've done. So here's an example. If I have the following is an example of a context-free grammar, which we will call G1. And we have these 3 rules here. In this case, it's not S. We have A as our starting non-terminal. So A yields 0, A1. So it looks like this time our non-terminal symbols are A and B, and our terminal symbols are actually 0, 1, and we also have a C down here. So it's kind of an unusual thing, but we have 0, 1, and C. So you notice the first production rule says A yields 0, A1. A yields B, so that basically is just one non-terminal yielding another non-terminal. And then B yields lowercase c. So we've got 0, 1, and lowercase c as our terminals. So we can see that the grammar generates words such as the string 000C111, okay? Because this is one of those, it's growing from the middle type things that we saw before. We could keep applying this one, this top rule where it says A yields 0, A1, and every time that A gets replaced, it gets replaced with a 0, A1. That would mean that the zeros are going to grow on the left side, and the ones are going to grow on the right side of the center as it grows. And eventually, you can actually have it replace that center A with a C, lowercase c. So basically, this is the language of 0 to the n. If we want to show it in a set builder notation, we can do that. It's not a regular expression. Set builder notation is acceptable. We can say that it's 0 to the n, c, 1 to the n, such that n is greater than or equal to 0. Meaning we can have 0 or more zeros and ones on each side of the c, but there's going to be the exact same number. Okay. And I think we're going to call it a day at that because I want to kind of save more examples for Thursday. We are at least the 24, 25 part. I would like a couple of you to remember, in case I don't remember, could you please write down that we ended at slide 24? That will save me some, my brain some storage. So slide 24. Are there any questions before we call it a day? And I upload this thing. Slide 24. Yes. Yes for us. Thank you. It'll be more important on Thursday. Okay. You are dismissed. If you have any questions for me, feel free to stay on. I'll be sitting here for a few more minutes. So you're dismissed. Yes. Note to Thursday BAW. Yes. Start on slide 25. Yes. Thursday BAW isn't here yet, so you're gonna have to remember that. Okay. Quiz worth more points this week? I'm not sure. Some of the quizzes, there's a variety of points on it. Some of them are worth more than others. Right. Yeah, some of them are worth like I think closer to 20, some are like 10, 15, some are 25. I think it's usually in that range. I don't think it goes over 25, but I'm not sure. Yeah, they're kind of in that range. Have a good one. Yep. Okay.
Doctor, I have a question about the
Yeah.
quiz.
Okay, one second. Let me just stop the screen share and the recording and then we'll take it offline. Okay. 1 second.
Yeah.
Just
What
a minute.
happened?
Just a minute. 1 minute.
All right.
Okay. All right, give me just a second. Okay. Wait a minute. That's not going to do it. Trying to find the recording. It looks like they moved the stuff. 1 second. That isn't right. Huh. Oh, there it is. They moved it. Yeah. Okay. So I'm going to stop the